Theory seminar. Today we have Benjamin Lovitz with us, who will give a talk on Chow decomposition. Benjamin is an assistant professor in the CSSE department at Concordia University, Montreal. Before this, he was a NFS postdoc and Zelewski Fellow at Northeastern University. He obtained his PhD from University of Waterloo in applied mathematics under the joint supervision of William Slofstra and John Waters. He has worked with problems which come from tensor decomposition, quantum information theory, and optimization. Over to you, Benjamin.
Okay, thanks. Thanks for having me. Thanks for showing up. So I'm going to be talking today about joint work with Alexander Tavera Blumenhofer, who's a postdoc in Copenhagen. Okay. All right, so let me just check something. So this talk is going to be about tensors and tensor decompositions. So a tensor is the generalization of a matrix to so a matrix is a square of numbers. A tensor is a cube of numbers. Okay, so you have some cube, some n by n cube, and in each of these n cubed entries, you have a number. Okay, and then a decomposition of a tensor is an expression of T as a sum of what we call product tensors. Okay. So what is this? What is a product tensor? So what do I mean by this? This is the tensor whose these three are vectors, AI1 and AI2 and AI3. And this is the tensor where, so the definition of this product, if you have three vectors, u, v, and w, three n-dimensional vectors, this is the tensor whose I, j, k entry is the ith entry of u times the kth entry of v times the kth entry of w. Okay, so three coordinates for our three-dimensional object, and yeah, so we define these as product tensors, and we want to know the minimum number of product tensors we need to express a given tensor. And so this is called the rank. R of t is the minimum R, such that there exists decomposition. Is this much clear? Okay. So there are some applications of this. I won't really be talking about applications, but just to have in mind, there's algebraic complexity theory. Quantum entanglement. And statistical machine learning. And I'll actually, I'll mention just a little baby application of statistical machine learning, just so you can see it. So this application of statistical machine learning is very quickly, it's you have this these four random variables. And I draw this picture, it's not very precise, but you have these four random variables, and it's like L is like giving rise to these to the other three. Okay, it's like the latent random variable giving rise to A, B, and C. Meaning, so you have these four random variables, and you have this assumption that conditioned on the outcome of L, A, B, and C are independent. Okay, so you have this assumption that the probability of outcomes little a, little b, and little c for the random variables big A, big B, and big C, condition on an outcome L for the latent variable L, is these are independent. So it's the probability of A given L, the probability of B given L, the probability of C given L. Okay, so it's an assumption, and the problem is the question is you're given the full joint distribution of A, B, and C, so you can like measure these guys, and you want to infer what the latent random variable was. So infer the full joint distribution from just your observation, just this assumption, and your observation of the joint distribution of A, B, and C. And one way to do this is through tensor decompositions. So you can write out, we just expand over the outcomes of L. Okay. So I'm not really doing anything yet. I'm just expanding this probability vector over the outcomes of L. I haven't done anything crazy. And then now I'm going to use my assumption, this conditional independence assumption. And what that conditional independence assumption tells you is that the joint probability vector is a product vector. So the probability of A given L, and so the probability of B, L, so C. Okay. Because right, the tensor product is the IJK entry is the product of the three. And here we have the ABC entry is the product of the A entry of, yeah. So by finding tensor decompositions of this guy, this gives you this corresponds to a choice of latent random variable. For each choice of latent random variable, you have a choice of decomposition. And let's say you're trying to find the latent random variable with the smallest number of outcomes. That would correspond, that would correspond to the tensor, the minimum rank decomposition of the tensor. I'm fudging things a little bit because probability vectors are non-negative. We're not just putting in arbitrary elements of Cn, but this is the idea how this works. And a really nice property of tensor decompositions is that the rank decomposition can actually be unique. It's possible that there's just one. So instead of right, it's possible that multiple latent random variables could have given, multiple choices could have given rise to this data. But if the decomposition is the unique rank decomposition, then this would uniquely infer a latent random variable. Okay. This is something you wouldn't want to do this if there wasn't a third random variable, then you would have this sort of analogous thing, you would never get uniqueness. So this is a nice thing about tensors that doesn't happen for matrices, like the analogous sort of matrix decompositions. Okay. Are there any questions? Yeah.
So they're assuming that the probability of L would be uniform in this case?
Ah, thank you. Yeah, I messed this up. Yeah, probability of L. Very, thank you. Great. Yeah. Okay. All right. So this motivates us to, right? So we're only handed this. So it motivates us to find decompositions of tensors, find them, and to certify their uniqueness. Right? So there's two. And today I'm going to be presenting both like algorithms and uniqueness results. So Yenrik's algorithm is misattributed to Yenrik, but everyone calls it Yenrik's algorithm. It's these ideas have been around since like Polya in the early 1800s, and then rediscovered many times since then. I'm just going to call it Yenrik's algorithm. So this is an algorithm for decomposing tensors. So suppose that T is a sum of AI1 to N, where the linearly independent for all j is 1. But yeah. So let me know if I'm writing too small. But so in a particular case where T actually has its rank is equal to N. So it's I didn't mention this. So this is living in T is living in this is N by N by N tensor. So if it has an expression of this form where all these first vectors are linearly independent, they have to form a basis for Cn, and the second and the third similarly are linearly independent. Li means linearly independent. Then we actually have an algorithm for finding this decomposition. If we're promised that this is the case. Okay, so then the rank of T is equal to N. And this is actually the unique decomposition. This is the unique rank decomposition. I'll write it out. This is okay, the rank is n. This is the unique decomposition, and we can find it. And we can recover it from T in order n to the cube, n cubed time, which is the best you can hope for, really, because you need n cubed time to just look at all the entries of the answer. So now I'm going to present the Yenrik's algorithm. So for a vector in Cn, I'm going to let Tf the F transpose tensor identity acting on T. So by this I mean, so I'm going to think of this as a matrix. So I'll explain what all this means. So what do I mean by this? If I have my tensor over here, this is called the contraction of T. I have T over here, and I write down, I'm gonna like write down the entries as like a sequence of n matrices. So I'm gonna write it as like A1, this matrix A1 on the face, it's an M by N matrix, dot, 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 and then the last one is gonna be AN. So it's gonna like the writing is like a list of n matrices stacked on top of each other. Then what this product is, this TF, is like, so just like you can hit a matrix with a vector, you can hit a tensor with a vector too. So I'm hitting this with a vector. What you get out, the definition of this product is I'm taking the matrix A1 times F, dot, 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 AN times F. And this is an n by n matrix. So that's what TF is. So this is an important, this is going to be important for us. So for example, in this case, for us, F is a sum, I equals 1 to n, of the inner product of F with AI1, AI2, AI3. This is what you get. And this inner product is always just going to be the bilinear form 30. And now an observation that the rank of this matrix TF is strictly less than n, if and only if F is orthogonal to one of these AI1s. A11 perp, N1 perp. So this is not hard to see because so for us, right, we have this assumption that these guys, all these AI2s are linearly independent and all the AI3s are linearly independent. So if all these were non-zero, then this would be a full rank matrix. And then, yeah, the only way it can be not full rank is if one of these inner products is 0. All right, so here's Yenrik's algorithm. All right, so I'm going to choose two vectors in Cn at random. And solve this matrix pencil equation. I'm going to solve for lambda, for which this determinant is 0. So this is a univariate polynomial in lambda, so this can be done efficiently. Or alternatively, this can be just done with a yeah, by multiplying by the inverse of TG, you're just asking what are the eigenvalues of TG inverse times TF. Okay. So this can be done in order n cubed time, or if even, yeah, n cubed time. And the key point here is that, so first of all, let me mention that this is equal by linearity. This is actually TF minus lambda G. So if you plug in F minus lambda G to here, right, these are the same thing if I look linearity. And then if you notice, these are, right, this is a two-dimensional space, the span of F and G, right? And so a two-dimensional space will have to intersect each of these n minus one dimensional spaces somewhere, right? So this, you know, there will be actually n solutions, n solutions, lambda 1 through lambda n, where h, I'm going to set, well, f minus lambda I g is in AI1 per. Okay, so it's a two-dimensional space. It has to intersect each of these things. When it does intersect this guy, it's going to have be reduced rank. And so the determinant will be 0. So yeah, you'll get these n solutions corresponding to these guys. Okay, and I'm going to give a name to the 0 eigenvector here. Okay, so let xi be the 0 eigenvector, the 0 e vector of TF minus lambda I G. Okay, be the thing that is the thing in the kernel. Okay, sorry, I switched that in there. Okay.
Sorry.
Yeah.
Say again. You say it's the 0 function.
Sorry, it's the 0 eigenvector. Yeah, it's the element of the kernel. Okay, so note that you take a, sorry, yes, AI3 times x times xj. Okay. Okay, so I'll write down what you get. You get 0 if I is not equal to j. Okay. The reason for this is that, yeah, when you're coming in with this f minus lambda ig, right, you're a matrix that is, you know, its inner product. This inner product is 0 for in the ith place, and it's non-zero everywhere else. And then xj has to 0 out that guy. So it has to 0 out each of these. These are, you know, we have linear independence here. So it has to 0 out all those guys. It has to be in the kernel. Right. Okay. And then, of course, it has to be non-zero for I equal to j, because xj is a non-zero vector, right? So it has to be, if it was 0 for everything, then xj would just be 0 vector, because these AIs span the whole space. We have inner product 0 with everything. Okay. Yeah, any questions about this? This is it okay? Great, okay. So we write this as a matrix equation. We have the AI1, A11, A13 through AN3 transpose times the matrix X1 through Xn is some diagonal matrix. And right, these are the guys we want, right? And we have, yeah, we don't know D, we know X, we don't know D. I'm going to multiply by X, by this thing inverse on both sides. So A13 transpose is equal to D times X1, Xn inverse. So um, 1 over D11, A13, 1 over D and N. Now I'm multiplying by D inverse on both sides. A(n)(3) transpose is equal to X1 through Xn. Okay, just manipulating this. And so this actually uniquely determines these vectors A13 through AN3 up to some scale, up to these T's, right? Because we know these eigenvectors, algorithmically we found these eigenvectors. Okay, so this uniquely determines A13 through AN3 up to scale. It's okay. And this is the best you can do, right? Because actually, yeah. So when I said uniqueness, I didn't actually tell you what I mean, right? So I meant uniqueness up to reordering the sum ends, right? Of course, you can shuffle around which one comes first. You can, but you can also do things like you have a product vector, then you can rescale the individual things. So this is equal to alpha u tensor beta v tensor 1 over alpha beta w, right? So there's a scale ambiguity even for that. So this is the best you can hope for. Okay, so this now you've recovered the A13 through AN3. Similarly, you can recover A12 and then A2. You know, I'll leave it there, right? The rest is homework. How would you find the rest of this decomposition? Okay. Any questions about the Yenrix algorithm? So I'm going to change the question now. So I'm going to talk about these things called Chow decompositions. And this is a notion of tensor decomposition for what's called symmetric tensors. So symmetric tensors generalize symmetric matrices. So a symmetric matrix we have this notation S2 of Cn. So it's just an n by n symmetric matrix, and I write this notation to mean that. It's it's just a matrix where the ij entry is equal to the ji entry for all ij. A symmetric tensor is similar. We again have our special notation, call it S3 of Cn, and it's a tensor for which T of I1, I2, I3 is equal to T of I2, I1, I3 is equal to dot 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 is equal to basically any way to permute these indices, sigma of 1, I sigma of 2, sigma of 3 for all sigma permutations on 3 letters. Okay. And then one type of decomposition for symmetric tensors that are, sort of have some similar applications as I mentioned before for tensor decompositions. These are called Chow decompositions. So Chow decomposition. So this is writing your tensor as a sum of what's called the Chow product. to R. Okay, so this is a little funny. I now, instead of a tensor product symbol, I'm just not writing anything at all. Okay, and so inherent in here is a little dot, but I won't write it. And what that dot means is the following. So AI1, AI2, AI3 is by definition the following symmetric tensor. It's basically you take it's exactly this. You take a product tensor and you symmetrize it. You project it onto the symmetric space. So, and what happens when you get that? When you do that, you get the following. Sigma in S3, AI sigma of 1. And we define the Chow rank, which I'll write CR of T to be the minimum R. Okay. So I'd like to mention, this is sort of an aside, that symmetric tensors can be identified with homogeneous polynomials on n variables. So this would be degree 3 homogeneous polynomials on n variables. So I'll just note this. You can, we won't need this, but these are isomorphic. And what the isomorphism is, you send a symmetric tensor to the polynomial f of x, or I should call it p of x, given by the inner product of t with x tensor 3. So this is a degree 3 polynomial, if you view it. So this is actually an isomorphism. Okay, and under this isomorphism, the Chow rank 1 terms become products of linear forms. So yeah, so AI1 gets sent to AI1 of x, AI2 of x, AI3 of x. So if you view everything in this way, you're trying to decompose a homogeneous polynomial into a sum of products of linear forms. And this gives you an efficient way to evaluate that polynomial, right? If you had a few number of linear forms in the decomposition, it would give you that would be an efficient way, a more efficient than just writing out all the coefficients of the polynomial value. So that's one application of this, and it shows up in algebraic complexity theory. All right, so how are we gonna? What am I doing now? So first the result. So we have basically a Yannerix algorithm for Chow decompositions. So we have a T. So sort of similarly to, it's very analogous to the Yannerix algorithm. We're assuming that our tensor has a decomposition of a certain form, and then we're showing that under that promise, we can find that decomposition. And the form that we're assuming is that, you know, it's a Chow rank R tensor, and we're living in S3 of C3R. And these, if you take all these vectors, all these 3R vectors, they're all linearly independent. Okay, that's basically, it's like kind of the most trivial thing, like the easiest thing you could think of that you should be able to find a decomposition. I equals 1 to R, J equals 1 to 3. All these 3 R vectors are linearly independent. Okay. Then the Chow rank is R. Is R. Uniqueness holds. This is the unique Chow rank decomposition. And we can find it in time, in order n cubed time. Right, n is 3R, so this would be 3R to the third. So this is the dimension of this space is order 3R cubed. So it's I guess I can just write R cubed, order R cubed. Dimension of the space is order R cubed, so this is basically the fastest you could hope for. It takes you the same amount of time to look at the tensor as it does to decompose it. Just like Yannick's out.
Question?
Yeah.
Do such decompositions show up in statistical machine learning? Like, or anywhere else?
Not that I know of. Yeah. Actually, wait. I mean, Arvind has some, but no, I remember asking him this question. He didn't know. So I think it's just algebraic complexity. Yeah.
I'm a little confused with the dimensions here. So now you want all 3 sets of vectors to be linearly independent?
I want the entire, I'm taking, so there's R terms in the sum, and there's 3 terms for each, there's 3 vectors, and I'm taking all 3 times R vectors, the entire set.
This is different from the previous algorithm in terms of like we had 3 sets of linear
Exactly. Yeah.
vectors.
The problem here, like the reason why this is like somewhat reasonable is because when you expand out the Chow product, all of these guys are showing up in the first factor, right? So they're all like contributing there. Yes.
So the Chow rank, is that the same as the rank for a symmetric tensor? Or maybe
No,
6?
not the same. You can already see it here. So this guy has Chow rank 1, but it has tensor rank. Well, it depends on how these are related to each other. Yeah. Yeah. Okay, so basically we're going to follow the same formula as Yennert's algorithm for this. So first, and I'm gonna make it a little more formulaic. So I'm going to define this contraction variety. So let xt be the set of linear forms such that the rank of TF is less than 3R. So it turns out that generically, if you just plug in a random point f, random vector f, the rank as a matrix, right? It's a symmetric tensor, but I can view it as just a tensor, and I can do the same contraction things before. The rank will generically be 3R. But yeah, I'm defining this as the set of vectors where the rank is strictly less than 3R. And then the lemma that makes this all go is that this, what we call the contraction variety, let me write that actually. The lemma is that this contraction variety, so from before, in the Yennerk algorithm case, the contraction variety was the union of all these perps, these Aij perps. And the same thing is true here. It's actually the same contraction variety. Xt is the union I equals 1 to R of AI1 perp union AI2 perp. Right, not exactly the same, right? For the generics, it was just the union of the AI1 perps, but. And then like, you can sort of start to get some, you can sort of believe me, right? That once we prove this, we're well on our way to getting a decomposition algorithm. Because we have the structure and we run a similar thing as before where like, yeah, you solve this this generalized eigenvalue problem and you know, you're gonna get all these eigenvalues corresponding to these different things. It's like the same sort of things before. Once we have this structure for the contraction variety, yeah, it works well. We're gonna get an algorithm. Okay. Okay, let's prove it. I'm not sure. I think I will prove it. Okay, so let's let MI be AI1, AI2, AI3. So TF is the sum of MIF. Okay. I'll take the contraction of these MIs. Yeah. All right. So first of all, notice that the image of TF is equal to the direct sum. Like these live in direct sum with each other, right? Because all these vectors, since all these vectors are linearly independent, they're supported on disjoint spaces, and so so the image will be the direct sum of these image of 1F and RF. This follows from the assumption that all these AIJs are linearly independent, right? So these spaces don't intersect each other. So F is an XT, if and only if F is the rank of MIF is less than 3. Less than 3 for some I. Okay. So the rank drops if and only if, since these are supported on disjoint subspaces, on spaces in direct sum, the rank is the sum of the ranks, right? The sum of the rank of M1F, the sum of so the rank drops below 3R if and only if the rank of one of these guys drops below 3. So generically, it'll be 3, and yeah. So by symmetry, so I just need to prove that this guy. It suffices to prove that the contraction variety of MI is AI1 perp union AI2 perp union AI3 perp. The things that make MIF drop rank is MI drop rank is exactly these things, and then okay, so by symmetry, rather, yeah, GL3R symmetry, right? We can assume that that MI is E1, E2, E3. Okay, so this is just a symmetry argument. Like these are three linearly independent vectors. I can find an invertible map that sends AI1 to E1, AI2 to E2, and AI3 to E3, and doesn't mess anything. And so let's just see what we get when we contract mi by f. By m by f. Okay, we have a 1/3 factorial. And then good, it's still here. So now I'm taking all these things. So for example, the first term is going to be the inner product of f with E1. F with E1 times E2 tensor E3. And then, okay, I might as well throw in the thing where we permute those. So E2, E3 tensor E2 plus, etc. Okay. What you're getting, I'm just contracting this big thing. And then when we write this out as a matrix, 1/3 factorial. Okay. Yeah, notice this, if we look at this as a matrix, sorry, this, I'm doing this whole thing as a matrix, so I'm not using tensor products. E3 transpose, E3, E2 transpose. So this is a matrix with F, inner product of F with E1 in the 2-3 entry and in the 3-2 entry. So, so we end up with is the following. This is F with E3, F with E3, F with E2, F with E1, F with E1. Okay. So this is what you get. Notice like inner product of F with E1 shows up in the 2-3 entry, the 2-3 entry as well as the 3-2 entry. And so the determinant of this is 1/3 times the product of this. So 3 factorial, it's actually, the determinant of this is 2 times, anyways, what you get if you work it out, you get the product of these three, 2, 3, which is 0 if and only if F is in E1 perp or E2 perp or E3 perp. Okay. Great. So this proves the lemma. This proves the lemma. And then now I can tell you the algorithm.
Basically, the lemma which we gave it stuff I1, I2, I3, and I1, I2, I3, I4.
Right. So we have, yeah, so no, it doesn't, you just have to be careful about how big of a rank you're taking. But so, yeah, so, okay, so if everything is linearly independent, the lemma does not fail. And yeah, but moreover, we can do better than that. Much better, because that rank would give you like, right now, if n equals 3r, right, we're going up to rank equals n/3, right? We're up to n/3, and that would give you n/d. We get like n to the d. We can actually go up much higher to n to the d. So instead of like getting worse as you get higher, we can actually do better. See. So should I go like to the hour or what? How? Until till 4? What?
I don't know.
Oh wow. Okay. I won't go till 4:30, but I'll go maybe a few minutes over. But okay. So here's the algorithm. again, you choose F and G at random. And then you solve, do the same thing as before, solve determinant of TF minus lambda TG equals 0. Okay, again, this is the same thing as TF minus lambda G. Yeah, just linearity. And so note that, right, it's the same thing as before. You have these are codimension 1 spaces, right? These are hyperplanes. And this is a dimension 2 space. So this F minus lambda G, right? The span of F and G is a 2-dimensional space. So it has to intersect each of these guys. It has to intersect these things. And when it does intersect that, this determinant will be 0, right? The rank will be deficient. It'll be less than 3R. Okay, so we're going to get 3R solutions corresponding to these three. So get solutions. Lambda ij, I'm going to index them by I and j, where I is 1 to n, and j is 1, 2, or 3. Okay, and 0 eigenvector. So 0 eigenvector xij. Okay, of df minus lambda ij. Okay. I guess writing it in this form just makes it clear you can do this efficiently, because you just like invert TG and then solve the eigenvalue problem. And now, just like before, right? We just play games, and we try to find these AIJs in the most efficient way possible from these eigenvectors, right? We just have a lot of structure. We have that these HIJs are orthogonal to one of the I'm calling these HIJs. Let's call this I guess not. Anyways, we have a lot of structure, and so we just need some way to sort of find these AIJs. And so here's one way to do it. So this is step 2. I'm going to choose L at random, like another linear form. Okay. And then we have a proposition that the inner product of xi prime j prime with TL with xij is non-zero if and only if I equals I prime. Okay, so I'm taking two these eigenvectors. Right. Maybe I should mention this. So this the way I've indexed this, right, is that f minus lambda ij g is in aij perp. This is how I'm indexing these solutions. Okay. This is so it's easy to see that if I is not equal to I prime, then this inner product will be 0. Okay, so if I is not equal to I prime, so let me just say, so I is not equal to I prime implies the inner product of xi prime j prime with TL xij equals 0 is easy. So the reason, yes, this gives you one direction of this proposition. The reason why this is that like xij has to be orthogonal, right? Xij is like it's in the kernel of the thing, and the thing is a sum of it's like every other term appears except for the ith one. Similar to Yenrich's algorithm. So xij is like zeroing out everything except for the ith, perhaps the ith level, and then xi prime is zeroing at everything except perhaps the I prime level, and so you put them together, they're just zeroing everything. Okay, so this is, yeah, we saw something completely analogous for the Yandex case. Okay, and the other direction is just proven using a similar symmetry thing. Like you can just, yeah, I don't want to get into it. This allows you to, so this is a test, right? So when you solve this problem, right, you just get all these lambdas, right? They don't have these indices attached to them for you, right? They're just there. And the first thing you might want to do is break them up into subsets of size 3, right? Where along J, right? Find the eigenvalues that belong to each rank 1 term will give rise to 3 eigenvalues, and you want to put those eigenvalues together. And so that's what this first proposition is allowing you to put those eigenvalues together, because this inner product will be non-zero if and only if those eigenvectors belong to the same index. So yeah, so we can partition the eigenvectors according to I. The eigenvectors okay, according to their index I. We get sets of size 3. So 3. Okay. So now I'm gonna find a basis. So I'm sort of inching closer and closer to recovering these Aij. So it turns out that since I partitioned into along I, these eigenvectors, I can actually find a basis for these for the span of the Aij. Of AI1, AI2, AI3. Because actually this is equal to the proposition is that UI actually equals the span of TL xi1, TL xi2, TL xi3. So since I know, I can find, I've broken up my eigenvectors into triples, and then I can just apply TL to that triple, and it turns out I actually get a basis for the space UI. So why is this? Okay, so first of all, this yeah, maybe I should write this out. So the proof. So first of all, the inner product of x. I probably should have written this already. So xij with a I prime j prime is equal to 0 for all I not equal, whenever I is not equal to I prime. Okay, so this is like we wrote down a completely analogous thing for the Yenrik's case, and this the same thing holds in this case, because basically the resulting xij has to be 0 on this one, has to be in the kernel of this thing, and so it has to be orthogonal to the linearly independent vectors that are in this image. Okay, so TL so TL xij is guaranteed to be in UI for j equals 1, 2, 3, because it's zeroing out all the other terms, and like the only thing left is a term that's indexed by I, right? It's killing everything else. Is that okay? Okay. And so Okay, so we have one containment, and we have this containment. This is good. And then the other containment is just that, well, TL is, for generic L, TL is an invertible matrix. It's a full rank matrix, which I didn't prove for you, but it's true. Or maybe it's part of this, maybe that lemma, it's like, maybe it's just proven in that lemma, probably. It's part of that lemma. But yeah, so this is an invertible matrix, and so at the end, these are still linearly independent. You know, they're linearly independent going in because they're eigenvectors corresponding to distinct eigenvalues. So they're linearly independent coming out, so they have to be a basis for UI. Okay, so we have UI. Okay, so this is done. So this proves this, and then this by linearly independence. TL is full rank. Is it okay? Any questions? Okay, okay. All right, so now we could recover from here. We could be done. If we wanted to be lazy and we just wanted a polynomial time algorithm, this is actually enough because we can, so we can recover. So let pi I be the matrix, yes, be such that be the matrix. This is an m by n matrix, Mn. C be such that pi I restricted to UI is equal to the identity matrix on UI, and pi I restricted to UJ is equal to 0. So once we know we have bases for these UIs, so we can construct such a matrix. And then from there, we know that AI1, AI2, AI3 is equal to pi I tensor 3 acting on T. If we apply this thing to T, like on all three factors, okay, we're going to kill everything else, and then we'll just be left with, you know, it's the identity on UI, so we'll just be left with this guy. So this in this way we uniquely recover the components. Okay. But the problem is actually everything I've done so far takes time. You know, order R cubed. This is just solving linear systems, and here we're just working with this is a linear system of this is n by n matrices, and we're solving a system of doing an eigen decomposition of n by n matrices that takes time order n cubed, or rather R, yeah, and letting n be R figure out. But here, just multiplying this takes longer than that. You're multiplying a tensor by yeah, so basically you're taking like two tensors and you're multiplying, yeah, so this takes like time order n to the 9th. Which is a sad, definitely not linear in the size of the tensor. So it's n to the 9th because this tensor product of pi's is right. It's an n to the 9th by n to the 9th matrix, and then you're multiplying it by an n to the 9th dimensional vector. So that whole thing takes time ordered into the 9th. No, sorry. It's an n cubed by n cubed matrix. You're multiplying it by an n cubed dimensional vector, this t, that takes time. Oh, maybe n to the 6th. I think that should be n to the 6th. Anyways, it's still not in there. Any questions? And I'm going to leave it. I'm going to leave it at that. So I'm more clever. You can be more clever. Last step. Takes order n cubed. Okay. So you can be more clever than that, and yeah, just kind of play around with. You have so much structure here, and okay. So now let me talk about extensions. Yeah,
this the more elastic often uses linear independence of the AI. A1, A1, I2, I3, or it's just from UI it's I1, I2, I3 for any.
Yes, it still uses linear independence. You have to be careful when they're not linearly independent. And but we actually do that. We solve that. We look at that, consider that case as well. For the AI within each term, like these guys are not linearly independent, but the UIs are still in direct sum. And you get things like with the quantum computing folks, you get decompositions into superpositions of W states. Is an example of this. Okay, so first we can extend this to a higher order result. Okay, so suppose T happens to have a decomposition. Okay, and I'm actually going to take it to have, so now it's a big, I've only talked about three-way tensors. Now it's a big symmetric tensor. It's living in Cn tensor 2D plus 1. It's a symmetric guy in there, though. So that's 2D plus 1 Cn. We only consider odd order. We weren't able to, probably out of laziness, we weren't able to do this for even order. And the assumptions we need. So the first is very mild. N is at least 2D plus 1. 2. The set of vectors, Aij, I equals 1 to n, j equals 1 to 2D plus 1, is in general position. So what this means, general position means that if you take any set of n of these, any subset of size n, they form a basis for Cn. So that's what general position means. They're sort of maximally linearly independent, even though they can't be linearly independent because there's more than n of them. This should be R. And 3, the most important thing is what's our upper bound on R? So I should say, like Yenrik's algorithm, remember we did like, so Yenrik's algorithm, you get an n by n by n tensor of rank R, right? For Yenrik's algorithm. Sorry, n by n by n tensor of rank n for Yenrik's algorithm. But it turns out that you can have tensors of rank up to order n squared. And going from n to n squared is a very difficult open problem. The best known is like 2n. Okay, so ours is similar, right? None of this is going to go to the maximum rank or anything like that. The maximum rank would be something like n to the d. I guess we get something. So the maximum rank would be something like n to the 2d plus 1. We get this complicated expression, upper bound on R. It doesn't really matter what it is. So I'll write down minus 2d plus 1, choose d. Okay, it's a complicated expression, but what this is it's theta of n to the d for fixed d. Okay. Basically, if you, yeah, I take everything, I'm just going to assume that d is a constant, and then what's the scaling in n? Notice this is much better than if you assumed, right, the natural generalization of that statement would be you take all these Aij's to be linearly independent, like the entire thing. Right, if all these Aij's are linearly independent, then the upper bound you get would be like n over 2d plus 1. So the rank would like go down as you increase the number of factors, but this is much, much bigger than that. Okay. Okay. Okay, then this is unique Chow rank decomposition. And can be recovered in order n to the 3D plus 1 time. This is the theorem. So we go up to a high rank, but the time we take is a little worse than before because it's no longer linear in the size of the tensor, right? The size of the tensor is like n to the 2D plus 1. We take n to the 3D plus 1 time for this. But the first step, right, is the same thing as before. We write down this contraction variety. Same thing. So you take, so step 1, let xt be the set of f in Cn, such that the rank of Tf is strictly less than generic. Okay, so by Tf I mean, right? I'm contracting T by F, and then the result is going to be a 2D weight tensor. I'm killing one of the factors. Now I just have 2D of them, and now I'm going to view it as a square matrix. And then you're going to get a generic rank. If you just pick a random F, you're going to get some, with probability 1, you'll always get the same rank. It'll be the maximum rank. And then I'm going to let xt be the set of forms that make you actually have less than generic rank. All right.
I think you don't use it because determining the rank itself hard.
Yes, but actually we do use it algorithmically because we prove that this set is a union of codimension 1 spaces. And because it's codimension 1, you can, if you pick a generic 2-dimensional space, then it'll intersect all of those codimension 1 spaces, just like the same thing from before. Yeah. The really important thing, like algorithmically, basically this procedure that I've written down twice now is it will always work as long as you get a contraction variety that is a union of subspaces of like constant codimension or small codimension, because then you can solve, like you can solve, if you have a polynomial system in a constant number of variables, you can solve it in polynomial time. So the first, all right, so what's the first thing I'll write down? What do you think the contraction variety is now?
Union of these hyperplanes.
Union of the hyperplanes, exactly. Yeah. So that's the starting point. And then, and then we play games and we get and this is what we end up. This is the games we played. This is the best that we could do. Okay, so that's any questions about that? So one more extension I'll mention. So I'm calling it the non-generic orbit case, orbit theorem, which sounds like way more fancy than it is. It's really just the same thing as before. So you have, going back to the 3-factor case. Okay, I'm living in S3 of Cn. Okay. And now I'm gonna relax this condition we had before that all these AIJs were linearly independent. Okay. And I'm only gonna enforce that these UIs, the span of AI1, AI2, AI3, such that Cn is a direct sum of the UIs, U1, UI. So in particular, if all the AIJs were linearly independent, this would be the case. But you could have some cases where these UIs were actually like two-dimensional or one-dimensional. Like these AIJs actually aren't linearly independent. Then so the decomposition is no longer necessarily unique, but you can find it. A Chow rank decomposition of T can be recovered in order n to the fourth time. So once again, we're not quite linear. The games we played just didn't give us linear time algorithm, but so this case is different because there are some different cases for what these UIs could look like in this case. So what are these different cases? So AI1, AI2, AI3 could look like a few different things, right? Could be all right, so let me write it down kind of in a stupid way. It could be like could just be AI1 3 times. Could just be 3 vectors, and then you take their tensor product 3 times. Or it could be AI1 squared AI2. It's possible AI1 and AI2 are equal, but AI3 is not equal, or whatever. Or you could have AI1, AI2, and then AI1 plus some alpha, beta, AI3, AI2. Right, the third could be some linear combination of the first two, but none of them are equal. And then finally, you could have the case that we were considering before, which is like they're all linearly independent. Okay. So if I write this down, this is sort of I'm kind of like being a little sloppy here, but if I write this down in better notation, this is like these are orbits. These are orbits of different vectors. So this is a GLN orbit of E1 to the 3. This is a GLN orbit of the W tensor, E1 squared, E2. So this is the W. For the W state. Then the third one is the GLN orbit of E1, E2, E1 plus E2. And then the fifth one is the GLN orbit of E1, E2, E3. Where GLN is acting as G dot T is G tensor 3 acting on T. That's how the GLN acts on these symmetric tensors. So we have these different orbits. Each one could be, you kind of have to consider these 4 different cases. Yeah, you kind of have to consider them separately. There's a problem though. Yeah, so I emphasized A here because actually this decomposition may not be unique in this case. There's a problem. So here's the problem. So if you take E1 cubed plus E2 cubed, this is this actually has Chow rank 1. And how does it have Chow rank 1? Which orbit is it in? It's in the orbit of this guy, GLN, E1, E2, E1 plus E2. That's Chow rank 1. Why is this the case? Anyone know? Anyone have an idea? Why does this have Chow rank 1?
Factors
Yeah,
using the two root of unity.
exactly. Yeah, yeah. So this is if we view this as a polynomial, this is a bivariate homogeneous polynomial. This is a homogeneous polynomial in 2 variables of degree 3. Every homogeneous polynomial in 2 variables that can be factored into linear forms. Okay. Yeah, so you're factoring into linear forms. The product of linear forms corresponds to Chow rank 1. Okay. And this is an issue because now, our rank could be lower, right? If some of these, if 2 of these that lie in this orbit, then actually we can put them together and get a Chow rank 1 term. But with the real numbers, you can't do this because actually the factorization will always be complex. So if you have the real numbers, actually you don't get this non-uniqueness. Yeah. Okay, so this messes up our condition that the rank is R, and it also messes up uniqueness because you can do silly things like E1 cubed plus E2 cubed plus E3 cubed is equal to E1 cubed plus E2 cubed plus E3 cubed. Right? These are the same thing, but this is 2 different ways of writing this as a sum of 2 Chow rank 1 terms. So this thing, it turns out both of these tensors have Chow rank 2, but not unique. Here are 2 different Chow rank 2 decompositions. Okay. Okay, so this is why I guess I'm just kind of explaining this theorem and why these things show up. Again, the first step is to characterize what the contraction variety is, and it's more complicated. It depends on what each of these orbits are. You write down what the contraction variety is, and then you play games. Yeah. So here's a corollary to this non-generic orbit theorem. Let's say they're all W states. They're all W tensors. Okay, so suppose E is a sum of AI1 they're all E is a sum of some W tensors with the UI, which is AI1, AI2, the span of AI. These guys being in direct sum with each other, right? Such that Cn equals U1. Okay, then you actually don't have a uniqueness problem. This is the only uniqueness problem. So then you get that this is the unique. Chow rank decomposition or W tensor decomposition. Of T, or maybe I call it W rank of T, and it can be recovered in order n to the 4th. So that's all I have for you. Thanks.
Overall questions? There's the non-general case also generalized to range.
We didn't think about it. Yeah, because it was quite a headache to go through each of these cases and then higher order gave more. Yeah.
I'm just curious, why is this going on gently?
Sorry?
Why the name?
The contraction variety?
No, ungeneric or
Oh, because if you take a generic Chow rank 1 vector, then it will then AI1, AI2, and AI3 will be linearly independent.
Oh, okay.
And so I'm calling it the generic orbit. Yeah.
With no further questions, let's thank the speaker. Here's the topic.
Oh my God. Thank you
Yes.
so much. Wow, thank you. I've never gotten a gift at the end of the talk.
That's more incentive for you to give out.
Yeah. Come back on Monday. Oh, wow. Thank you so much. Awesome. Well, I was kind of jealous of your moment, so I got one too. But it's yeah, no, good for you. Thank you.